Introduce to you Dr. Yuankai. Whoa, hopefully I got the name correct. He's got a PhD in EE and computer engineering from Vanderbilt. He is a professor of same at Vanderbilt. He's also got a second appointment at Vanderbilt where he is, I did not write down what your appointment was, but he studies pathology, microbiology, and immunology. He is the director of the Biomedical Data Representation and Learning Lab and focuses a lot on multimodal data analysis. Hopefully that was adequate, sir.
All right, thank you for the introduction. All right, so, hey, good morning. Yeah, all right. My name is Yuankai, last name Hu. Actually, it's very easy to remember right now because yuan is Chinese currency, right? US is dollar. If you visit China, you will use yuan. And previously, it's hard for me to introduce Kai, but now Donald Trump had a granddaughter. Her name is Kai, so it's very easy to introduce now. Okay, Yuankai. Okay, so how many of you guys are students here? Can you raise up your hand? It's about half. Yeah, if you're a student, probably my relationship with TSU is longer than you guys because my wife did her master's degree in computer science at the TSU back to like 7, 8 years ago. And she took class from Professor Seckman, Professor Arnaz, Professor Rogers, Professor Yao. I can easily tell like 10 different professors' names in CS department. And I still remember I dropped her off because at that time I was a student. We were so poor, we only have one car. So I need to drop her off, go to my campus and pick her up, then go back, etc. Okay, so yeah, I'm super familiar with TSU campus. Okay, today we will continue this amazing workshop. I think I looked through the content that you have covered yesterday. There are a lot of beautiful math series. And today, my presentation or my lecture is more about the application side, especially the computer vision side. So have you heard about the terminology called computer vision? Yeah, so in general, machine learning or AI is trying to mimic our capability. So if they mimic our learning capability, it's machine learning. They use machine to mimic our learning. And the computer vision is the technology to mimic our visual system. And today we will see how can we use the knowledge you probably learned yesterday or from other classes to do some machine learning task for vision. Okay, hopefully this works. Presentation? Oh, okay, I see what you mean. Okay. Okay, approve. Something like this, okay? Oh, all right, great. Okay, and this is the content of today's class. We will first introduce a little bit about fully connected neural network and convolutional neural network. Then we will go to some basic computation of convolution. And those are the key components in convolutional neural network. And then we'll have some demo and the practice. Okay, I probably have some demo in the middle as well. So let's see. All right, so let's continue going. Okay. Yesterday, hopefully you have already learned the concept of neural network and fully connected neural network somehow. Okay, so actually neural network is not a new concept. It has been there even back to like 20 years ago when I was undergraduate student. We already learned neural network, and it's probably have a history of 60 or 70 years. And today, when you talk about AI deep learning, people talk about deep neural network, okay? And this figure shows the difference between a neural network and a deep neural network. So can you tell the difference? Yes, so many numbers of layers, right? So the deep just means more layers, okay? There's nothing fancy. And can you imagine why we have this deep network right now rather than like decades ago? Why do we have that right now? Yes, we have better hardware. Like when people play video game, right? So you probably want to buy a cool GPU card, right? And at some point, back to 12, 13 years ago, some smart people figure out a way to use GPU card to run the neural network. And suddenly now we can run hundreds of layers of neural network, which was impossible before we had the powerful GPU card. Okay, so if you have a GPU card for gaming, you can use that for deep learning as well. Okay, yeah, before I go to the convolutional neural network, let's see the fully connected neural network a little bit. If you have learned the neural network before, okay, so this is just the layer of nodes, and all the lines you see in the middle are basically elementary level math with either plus, okay, or multiplication. Okay, so this is the components. And if I zoom in any of these nodes, okay, you will see something like this. Oh, maybe another, oh, here. Yeah, if I zoom in any of the nodes, okay, you can see, oh, this one is this guy. Over there? Yeah. Okay, okay. All right. Okay, so you see a lot of nodes, you see lines, you see something like this in the network. If I zoom in any of the component, if I zoom in, make it this big, okay, so if you, so the scene you see is like this, and with some other connections, okay? And all these outputs are the same. So have you learned this? No? Yeah, this is called a perceptron, or you can just say this is artificial neuron, okay? Neuron, right? So this is very similar to how our brain works. So in our brain, we have a lot of neurons. Neuron connect to neuron, neuron connect to maybe hundreds of thousands of neurons, and we pass the signal from one brain region to another to do the computation. So this is the artificial neuron that mimics our human brain, okay? And here in the middle is a sigma, and on the right side, there may be or may not have an activation function. And for each line here, you have a weight, okay? And you have your x. All right? And for each node, what you do is basically W1, X1 plus W2, X2 plus W3, X3, and you get this Y. And if you have the activation function, you basically have additional nodes in here. But it's just the elementary school math, weighted sum, okay? So it's amazing, actually, right? So if you see the network, they're all elementary school level math, but when you assemble them together, you can do Tesla, self-driving, you can do all this cool stuff, okay? Because this is kind of basically how our brain works. Okay? And you might not realize like our brain is actually still the best computer on this planet, right? If I give you, yeah, we have chicken biscuit and egg sauce biscuit, right? If I give you that, you can do computation for the entire morning, do the learning. But if I want the computer, today's computer to do that, I probably need to have thousands of watts or whatever to do this computation. Okay, I probably need to build a super computer center to do the similar level of computation. Okay, and if we understand this, linear combination, then I can train a classifier, which is a prototype of deep neural network, to do this classification. Okay, so I give an example. Say, well, so if I ask a student, okay, I randomly ask student in Nashville, give them a pool, say, well, which state are you? Right. So most of students say, I study in Tennessee because I do the pool in Nashville. I say how good your baseball team is, how good your football team is, right? And based on these features, you can do this neural network and classify if student is from Vanderbilt and TSU, right? If you ask student and the student say, yeah, our baseball team is great, but the football team is really bad, then that's probably a student from Vanderbilt. Okay, so we can do things like this. Okay, you can see there are a lot of this kind of linear combination in the middle. Okay, and well, actually, before people have convolutional neural network, we can already use the same neural network that we use for this questionnaire classification for image. Okay, so for example, if here is a picture from TSU, well, without convolutional neural network, I can still do this classification, say this picture is from TSU. Okay, so here is the strategy. Can you tell how can I learn this two-dimensional image with this very canonical deep neural network? Yeah, so can you see what's going on here in the middle? Yeah, those are the position, right? So here we probably have like I don't know, 20 by 20 pixels. But if I simplify this to 16 big pixels, so the way we can do is that we can stretch the image to a long one-dimensional signal. Okay, remember this network, fully connected network, can only take one-dimensional signal. Well, to learn image analysis or computer vision using this network, we need to stretch the image to a very long one-dimensional signal. Okay, and well, people do that. It works in many cases, but it has some bottleneck. Taken the middle?
Yeah, we were trying to find out what the
Yes, okay. So think about it, we have an image, right? Yeah, that's a really great question, actually. So if we have an image, right, the thing you see behind the image are the pixels, okay? Pixels, okay? And how many pixels depends on how good your TV or computer is, right? You see like a 1080p, right? You have 2K resolution, 4K resolution, means the number of pixels, right? And if I number the pixels from 0, 1, 2, 3, 4, then you can have the location of each pixel. Here, I oversimplify this to just 16 pixels, but in reality, you have thousands of pixels. That make sense? Yeah, and yeah, you see a picture as picture, but if you zoom in big enough, they are all like pixelized. And you see basically either a single value between 0 to 255 if you do grayscale image, or you will have 3 of these numbers if you do RGB, red, green, blue. Okay, so these are numbers. And we can basically extend this image to a very long one-dimensional vector and still use the fully connected neural network for computation. Okay, so then why convolution, right? So why we want to do convolution? Well, this is actually from neuroscientists. So if we see the history of AI, deep learning, a lot of contributions are not made by computer scientists. Actually, a lot of contributions were made by neuroscientists. Like there is a group of people in cognitive neuroscience try to understand how humans understand the visual signal. Okay, so for example, if I ask you, all right, so what is the color of this flower? Pink, right? And in your brain, probably you are doing something like this, right? You will not pay attention to the color of the castle or how many people's behind, right? So you immediately see, oh, there is a flower and the flower is pink. This is amazing capability of human brain, right? Think about if you use a computer, if try to understand the picture, they will process basically all the pixels, right? But as a human, I can immediately see, oh, this is the flower, and I don't care about the things remaining, right? So based on this finding from cognitive neuroscientists, we say, well, probably we can define a better neural network than the fully connected neural network for vision task. And then we have the convolutional neural network. Okay, another test. What Sheldon is drinking? Hmm? No. What he is drinking? All right. Okay, and then ask how many cups are there on the shelf? No, on the shelf. Okay, so that's the amazing thing for human vision, right? So we can immediately see what's going on here, but we don't care about what's going on behind. So that's why if I give you a hamburger or sandwich, you can compute for a whole day, but I need 1,000, 10,000 more power for computer because they trying to understand everything, but it sometimes useless, right? That's the amazing thing for human vision. Okay, so here I first want to show some math, like behind what's going on. Okay, is the convolution, right? So you can see this is convolutional neural network. So convolution is the key thing. Okay, the convolution, and later I will cover the math. But the basic idea of convolution is that now we don't need to understand the whole image. Instead, we try to understand these small regions. You can see there is a window like sliding around the image. So those are the things we do the computation, which is region by region. We don't need to see the whole picture. We just want to see the diacode. Okay, and by defining different kernels, you can extract different features from the image. Okay, so now I will. Do you have a laptop or something like that? Okay, so yeah, let's see this demo. This demo is actually very cool for convolution. Let me, see. How to copy the text here? Okay. Okay, cool. Yeah, I probably need to move to that side, right? Okay. All right. Okay, great. Can you see that on Zoom? Oh. Yeah, maybe just screen to the side. Okay, all right. Okay. All right, cool. And you can find the link from the PowerPoint slide. And probably stand a little bit here. All right. Okay, so this is actually an active interactive demo. So first of all, as I mentioned, you see a picture, right? You see a picture, and this is the picture you see. And if you zoom in enough, you can see those are pixels. And on the left side are the grayscale values corresponding to each location, right? When you move, you can see there is a red window move, okay? And now this demo allows us to try different kernels, okay? So for example, you can click this and you can choose any of the kernel you want. And this is sharpen. And if you select this, they will generate an image from your original image on the right, okay? And if you move your mouse, okay, if you move your mouse, you will see some numbers are changing, okay? And you can see here, okay, so anyway, so here you have 3 by 3. This is the original image, and you apply the same kernel, right? 0, -1, 0, -1, 5, -1, 0. -1, 0. Those are the sharpened kernel, which means if you multiply these numbers to this 3 by 3 image region, you will see an output on the right. Okay, you will see some output on the right. So if you compute all these pixels in these dark regions, and you get an output. Okay, so this is how you get a sharpened image, just like you do in Photoshop or whatever tools you use. And you can try another. Okay, if you do this bottom Sobel filter, you basically try to extract the horizontal lines. See, and if you let's see, top Sobel, you are trying to get the top lines. Okay, and outline. Okay, so you can try different kernels. Okay, and this is how computer convolutional neural network try to understand the image. They will first tell, okay, so how can we understand that this is a whiteboard? I will first extract the feature, top border, top boundary, bottom boundary, left and the right, the color of the board. With these features, I will know this is a whiteboard. Yes. This one? This one? Oh, they drop on menu? These are just examples. Actually, there are thousands of, 10,000s of different kernels that we can use. And before we had a convolutional neural network, basically my first half of my PhD, we spent a lot of time to define all these kernels or filters to get the best combination to mimic human vision. We try to guess how human beings understand all the objects, right? Is that boundary, color, texture, etc. And how we get those features, we apply these kernels to the image. Yeah. Okay.
So I have done something related to this, but I like always confused that was kernel. What does that actually?
Oh, you mean this kernel? Yeah, kernel means filter. For example, I can give you some example. Okay, probably just use this side. Okay, so if you have an image, okay, if the image is just a line, okay, and then you can apply a kernel to this image, okay, yeah. Oh, this side. Okay, okay. Until, oh, okay. All right. So this is, okay, great. Which one? Oh, okay, brand new ones. All right. Okay, thank you. Okay. So if you have an image, the image is just a line, okay? And then now, if you want to find some feature in this image, you can design your kernel, okay? So for example, you can design your kernel as this and apply to everywhere in this image. Yeah, the right one is the size of this kernel. It's exactly the same thing I draw here. And behind the red box, there are 9 different numbers: -1, 0, 1, -2, 0, 2, and the -1, 0, 1. Here, I just draw another set of kernel. And if you apply the kernel to here, right, you will get something like 3, because this is 1, 1, 1, 0, 0. And you do the pointwise multiplication like this, add them together, you get 3, right? And think about if you apply the kernel to the entire image, you will get a feature map, something like this. Yeah. Yeah, so yeah, that's a great question. So probably I will introduce that in about like 10 slides. Let's start from grayscale, because it just has one channel, right? See this? And if you apply another kernel, okay? you will not get very strong signal. You probably get something like this. Okay, but if your image is like this, then when you apply this kernel to here, you get a very strong output. Okay, so by defining different kernel, you can extract the feature of horizontal line, vertical line, 45-degree, circle, whatever. Okay, yeah. Yes, that's a game changer. So in my first 2 years of my PhD, we spent a lot of time to define all these kernels, but deep learning is a game changer. Now, in today's convolutional neural network, the network will learn the best kernels for us to understand the image. And sometimes we cannot even understand why a computer choose these weird arbitrary kernels. So that's the amazing thing.
Once we train CNN, it will automatically determine the best kernel. This is the problem. Patient confusion, instead of kernels, there's something else like that detection from yesterday.
But already established problems can use it. But whenever someone is training a new model for their purpose, how they fix it? Is there any iteration or something? Any remedy of the same problem?
Yeah, so that's why you need to do the training, because, for example, if you're trying to build a vision system for self-driving, right, and you probably need to collect some real street scene image and train the model, right? And today, you probably heard the terminology called the foundation model or foundational model. The way they do is that they collect huge amount of data and they train the model. Since their model has already seen all kinds of pictures, it is generalizable for different scenarios. Okay, this is actually a game changer. That's a really great question. So the change from human-driven learning to data-driven learning is a huge game changer for the entire machine learning world. Like the ChatGPT you are using, they are doing the similar thing. Now, if I study natural language processing back to 12, 13 years ago, we spend a lot of time to define those rules to understand the text. Okay, if you see a question mark behind something, that means this. If you see a escalate behind something, that means that. We define thousands of rules to understand the human language, but it didn't work. And today, we just say, yeah, computer, learn the rule for us, and we have ChatGPT. Yeah.
Just like, what's that like?
Yeah. Yeah, typically you need to use hundreds, thousands of kernels simultaneously to extract different aspects of the image. And later you have another layer to further reorganize the feature you get. Then you have another layer to reorganize the feature you have, eventually give you the prediction. Right. Yes, multiple kernels for each layer, and you need multiple layers. So you need these two-dimensionality. Yeah.
We can train the model with large data.
Yes.
But currently, there are many machine learning models with very less number of data.
Yes.
So we need to activate in that case also.
Yeah, so, well, if you have a model has been pre-trained, then you can have fewer examples to fine-tune this, right? Just an example, if I have two kids, one kid have already learned keyboard for 10 years, another kid have never played any musical instrument. Then I say, hey, both learn piano. Can you imagine what would happen? The kids who play 10 years keyboard would probably spend 5 minutes or 5 days, well, to be more generous, 5 days, then the kids can play piano really well. But for the kids never play any instrument, probably I need to train the kids 2 years. So that's exactly the same principle here. If you have some pre-trained model, that now the big tech company, they release all these pre-trained model. If you already have a pre-trained model, you probably need a few hundred, few thousands of image to fine-tune the model just like from keyboard to piano, to make a great pianist. If you don't have that, unfortunately, you probably need to have more training data to train your pianist. Okay? Yeah, I think you had a question.
Kind of like three-dimensional.
The gray box. What do you mean gray box? The ID? Oh, the ID of the box? Yeah, so those are the location information, right? To tell you where it is. And for convolutional neural network, the good thing is that they keep the location of each patch so you know where it is. Okay. All right. And yeah, this demo is actually really fun because they allow you to do something that I did in my PhD, at least in the first 2 years. Okay. You can define your own kernel. You can put any number like -200 or whatever, and then you can see what's going on. Okay, so you can play with this. All right, so let me go back to the slide. Yeah, I know how to do that, so it should be fine. Okay, great. All right, so hopefully you enjoy this demo and see what's going on behind this convolution operation, right? And the key thing for CNN is that now we give the power of finding the best combination of the kernels to computer rather than do it by ourselves, okay? And this is also something very interesting from philosophy standpoint, okay? So if we are trying to figure out how we understand the things, right? You basically use our brain to understand our brain, right? So think about if we let ants to understand how ants work, it's very difficult, but we can understand them because we have a higher dimensional intelligence or higher computational power, right? We can understand the cat, dog, but if you ask a cat to understand the cat to do some research, it's impossible, right? So that's the philosophy trap here. So in the past few hundred years, we're trying to understand how we understand the things. It's hard. And today, we give this job to computer, and you can build a huge GPU cluster in Arizona, whatever. They have maybe 10, 100 times more neurons than our brain. Then they probably can figure out how we understand the thing. Okay, so that's also a very interesting standpoint from philosophy. All right, okay, so if we understand that, I can show you some example. Like this is how we did the research as a computer vision scientist back to my earlier stage of PhD. Okay, so if you Google image filters, you can find the Gabor filter, Swift filter. If you are old enough, like learn those old school computer vision concepts, you will see these are beautiful symmetry set of filters defined by human to extract different type of feature from the image. And later we assemble these features to the concept, say, there is a car or there is a Jeep, whatever. This is what we did, okay? But the limitation is that typically this does not perform as good as human, okay? And later, we have this game changer, which is convolutional neural network, okay? So now you can see they can learn these arbitrary kernels. And at the beginning, we try to understand the small regions in the image by applying all these kernels. You can see we can have horizontal lines, vertical lines, 45-degree, right? So like what we did just using this demo. And then we shrink this feature map about half and apply another set of kernel. Say, okay, if I see two curves, one circle, it's I, okay? If I see something like this, by adding or combining these features, I can find the nose, I can find the mouth, okay? And you can further shrink the image and apply all these filters to find, okay, this is a face, okay? And can you imagine how can we use this in our real life? Okay, so if today you have a kind of okay cell phone, you bring that to your face, and you can directly use that without putting the password. That is how it works. Okay, so they see your face, they assemble all these concepts using convolutional neural network, and they say, oh, it's the owner. Okay, so that's the idea. And those are very kind of different from the features that we learn as a human being. Okay, so I have another example here. This is how convolutional neural network understand that this is Audi A7 rather than a Mercedes or BMW. They will first learn these filters. Those are very local filters to understand that there are lines, rounds, circles, and then they assemble these concepts to the second layer to get these called the middle level features like wheel, window, door, etc. And then in the next layer, they have these high level features. Say, well, this is probably one of these cars. And eventually, if you find a good match, you can tell this is Audi A7. Okay, and today, all these things are learned by computer rather than learned by hardworking PhD students or scientists. Okay, so that's the game changer. And here, I want to first introduce the mass of convolution. Okay, so it's still the elementary level mass here, but now we apply this to two-dimensionality. Okay, yeah. This one? This one or? Okay, okay. Okay, okay, all right. Okay, this one? Okay. Oh, yeah, there is a button of mouse. Okay, okay. All right, so let's see. So hopefully, let me close the mouse. Error, okay, okay, great. So if you have the paper, you grab at the front desk, if you have a pen. So let's practice the math of convolutional neural network. So if you understand this, you basically understand almost all the math in convolutional neural network, okay? So now I can apply many filters, right? As I say, you can have thousands, 10,000 of filters. And these are basically 3 by 3 or 5 by 5 matrix. Let's practice just one, okay? So let's practice one, okay? So here I tell you, okay, this is some filter that I've already learned. This is my image, okay? Compare with the face image you see, I further simplify this to only 36 pixels, okay? And they're only 0 and 1 to make the computational easier. So now I apply this kernel to here. Now I give you probably 1 minute to see if you can get the value in the output. Sorry, oh, you don't need a minute? So it's, I say spend 1 minute, probably I need to change this to spend 5 seconds, something like that, okay? All right, 3, okay? So that's the math. Then, oh, okay. 3 point, okay? So anyone can tell me how? Okay, you have 3 by 3 there, 3 by 3 there. You, okay, make sense? Plus 0 multiply -1. Okay, 1 multiply 1, 0 multiply -1, 0 multiply -1. Then I write it here, plus 0 multiply -1, 1, 0, -1, 0, -1, 0, -1, 1 multiply with 1, okay? Okay, and if you see 0, you don't need that, 0, 0, 0, 0, 0, okay? Then you have 1, 1, 1, so it's 3, okay? So that's, yeah. Oh, that's no meaning. I just give some random number. I can put 2 or 0.5, doesn't matter. It's just example. There is no physical meaning behind those numbers.
So the filter was.
Yeah, from the local region of the image, just like we see Diet Coke for Sheldon, we just focus on that small region and extract the information from that region. Okay, so at the beginning, we start from the top left corner of the image, and then second step is move one step, and this concept called the stride. Okay, stride. You can understand this as step. Okay, and now I'll give you another 5 seconds. Can you tell me? 1? -1? Any else? We can do a byte. 0. Okay, -1. Okay, now I'll give you another 30 seconds to see if you can get -1. Oh, you mean how to get this? Or no, I mean the current one. So because I see 1, 0, -1. So I just want everyone get -1 here. Oh, you already go to the next phase? Okay, so let me see. Yeah, this one, right? -3. Yeah, again, another 10 seconds to see if we can get -3 here. No, this is, yeah, you are moving fast. Yeah. Everyone get -3 here? Okay, then congratulations, you understand all the math of convolution. They're just that simple, okay? And here I show you can do stride equal to 1 or 2. Probably I need to go back a little bit. Stride equals to 1 means every time you move just 1 pixel location, but you can apply stride equals to 2 to move 2 pixel locations each time, okay? 1 step or 2 step. But if you don't have any preference, 99% you want to do stride equals to 1, okay? You don't typically do 2, 3, 4. Yeah. Yeah, if they can further move to the right, they will go down to the top, to the left side and move down. You mean? Yeah. So a lot of people have already know that concept. It's called padding. So you can pad the zeros to the right to allow the computation. Yeah. Yeah. For you guys, you probably don't need to sit here. You already know the padding. Okay, great. All right, stride equal to 1 is the typical thing. Then you move a little bit, get a -1, -3, and you can get -1 here. Okay, so this is for the next line, okay? Since the stride equals to 1, you also move just 1 pixel lower to get this, this, and this, okay? So at the last computation, so if I give you this and this, what would you get? Okay, congratulations. So that's all the math. Okay?
So how can we know
Which order? Okay, so how do we decide these numbers, right? Yeah, this one is fixed. What you get, whatever you get, the picture, right? But how can we get these numbers, right? These are learned by computer from the training. Like how you learn all these weights in a fully connected neural network, this is learned from backpropagation.
Yesterday,
Yeah.
yesterday afternoon, Dr. Harden explained that you have a function, error function, W1, W2, right? Those W's are those weights. And we don't know them at the very beginning. Don't know what those weights are. Okay? And well, for regular neural networks, those weights, but for convolutional neural networks, each filter parameter is a weight. Think about it like one parameter that we need to determine. We don't know any one of them at the very beginning. So we start with a very bad filter, random filter. Random numbers, it will perform so bad, okay? But let's say that you want to do a plant detection system. So in order to have such a system, you have to train samples first. So you will say, okay, this is a kind of, tell me a kind of tree. So, what tree? Oak tree. Okay, so this is an image of an oak tree. Okay. And but you will tell the system, this is an image, and I know that's an oak tree, right? So it will pass through those randomly generated very bad weights and parameters, and it will generate a junk output. And then you will compare the junk output to what you expected. And that's your error function. That's like yesterday, Dr. Hardiman explained, that's the loss function of error function. You will say, okay, now I have this loss function. I need to do gradient descent. Remember yesterday, I will do one step coming closer to local minimum. So I want to minimize that error. I will come one step less in the right direction. And I will update all those weights and filter parameters little horrible, right? The next step, I will get second order. I will say, hey, this is my new image. What I expect, let me calculate the error. And based on what we learned yesterday, the error is supposed to go a little bit better to that local minimum, right? Then you will update the weights, filter parameters a little bit. Assume you have 100,000 of those images. Every time it gets a little better, go to local minimum, little, so you minimize the error. And you stop. And then you go back and look at the filter parameters. That is your filter. From this point on, then somebody's going to give you an image that you don't know what it is, who pass through from those filters, as Dr. Fu is explaining, then it will tell you that with 98% accuracy, that's a whole. You get the idea? So those parameters will come up with training.
Yes, exactly. Okay, so that connects what you have learned yesterday and with this one. So this is the same thing. These are weights. These are all these W's, but we just put it as 2D format, but literally it's W1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and you have really bad numbers. Actually, random numbers can be negative 0.4, then 2001, whatever at the beginning. It's really random. But after you train your model, many iterations, you converge. Okay, just like if I give you Steve Curry, right, and shoot a 3-point, it's a trend model, then you get like a 70% field goal or something like that, right? But if I train the kids from scratch at the beginning, he will just throw randomly to the basketball court, right? On the basketball court, they just throw randomly. And if they throw the two right, they know, okay, next time I'm a muscle. Those are the weights control your muscle and all the joints. I probably need to go this way a little bit and go that way a little bit. And you train the kids years, and hopefully he can or she can shoot 3-point. Okay, same principle. So now I give you Steve Curry here. But to get that, you need to do the backpropagation, as you learned yesterday, to get these filters. Okay, great. All right, so these are all the math. And typically, today, you don't need to worry about how to get this, because if you use PyTorch or TensorFlow, they do this optimization for you automatically. There is just one line of code. They will do this tied list for you to give you Steve Curry. You just tell the computer, now I want to shoot 3-point. This is my kids. This is my basketball court, okay? And you just run that one line of code, they will give you a Steve Curry. Okay, and now the thing that when you have a Steve Curry, this is how you shoot, okay? All right, and yeah, you can see filter are trying to get something like the pattern, like here I show like 2 patterns. One is horizontal line, another is vertical line. Here you can see the pattern is 45-degree diagonal. So in that case, interestingly, you see there are several big numbers here, 3, 3. And if you look at those regions, okay, they are trying to match this pattern, right? So if you follow the pattern of your filter, you get a large number. If you have some random patterns, you get smaller number. Okay, so this is how it works. Okay, those are two big numbers. All right, so now I have another filter. Okay, as I promised, I can use thousands or 10,000 of filters. Okay, I can do the same process as the first filter. What do we get here? Okay, and when I do the second filter, I save this to my computer memory. I no longer touch this. Then I have another set of these 4x4, -1, -1, -1, -1. Okay, like this. Okay, and you can see the second filter have the pattern very similar like the thing I draw here. So if there are some vertical lines in your image, you have very big response. Okay, and you can imagine if you do the third filter, you save this to the GPU memory or CPU memory, then you add another channel. We call this feature channel. You add another channel of feature. Yeah, that's a great question. Actually, we don't want to reduce the size of the image at this step. And the next step, we will have the pooling. Then at that time, we want to reduce the image size. And to keep, you can imagine, right? If you do this 3x3 kernel, you basically lose 2 pixels, right? And as the previous question, now you can pad the zeros around this image to an 8x8 image. You can pad all zeros around the image and apply this again, then you have a 6x6 feature map. See what I mean? So you add a 0 here, 0, 0, 0, 0, 0. So you basically, if this is your original image, okay, this is your image, you just add all zeros, 0, 0, zeros. And this is your new image. If the original one is 6x6, now you have 8x8. Okay, and then you can do the computation here. You can do the computation here, okay? And then you get 6x6 feature map. And your original image is 626, so you don't lose the spatial resolution. Okay, great. And those are feature maps. And this is the first layer. The first layer, you have the image at the input. But in the second convolutional layer, these feature maps will become your images, okay? I use quote image here because they are no longer the image that we understand. Those are just feature maps, but for the second layer, those are your images, okay? So then you apply the kernels to the second. So in the second layer, you apply your kernels on these guys. Okay, just keep going like this. Okay, so now we have 4x4 images, but later we will introduce padding so you can recover 6x6. Okay, so here is the difference between convolution and fully connected neural network. Okay, so again, I can stretch this guy to, this is 6x6, so it's 36. I can stretch to 1 to 36, put a 1 here, put a 0 here, put a third 0 here. Right? I can still use fully connected neural network, but you can imagine if you stretch the image to a long vector, first the issue is that it's expensive, right? It's that the dimensionality is very high. The second issue is that you lose the beautiful 2D connections between the pixels, right? If I stretch a Diet Coke to 1D and throw that to you, probably you cannot recognize it's a Diet Coke, right? So that's the limitation of this kind of learning. Yeah. Mm. Mm. Yes, that is the max pooling, okay? Yeah. This is called the max pooling. So you just pick the biggest number of each region. And there is another popular pooling strategy is called the average pooling. Can you imagine what's going on? Average pooling? Yeah, you get an average and as the value. And this is also key component in a convolutional neural network pooling. Okay, we will cover that. Yeah. Learnable padding. So you mean you add some parameters here and try to learn? Well, yeah, theoretically it's possible, and it can be a good PhD paper or something like that. But practically, you don't know what to add, then just add 0. Right? Yes. This is called an image inpainting, right? You can paint something in the middle or paint the surrounding area. You can paint anything, right? Okay, and you can see this is actually convolutional neural network is actually not a new neural network. It's just a sparse version of the fully connected neural network that you have learned, okay? It's not some 2D neural network, okay? It's still one-dimensional, but you can see it only have local connections because we now only compute the local region in the image, okay? It's a sparse version of fully connected neural network. So all the backpropagation you have learned yesterday can be directly applied to convolutional neural network. Okay, it's not a new mass in terms of optimization. Okay, so that's the fully convolutional neural network. All right, okay, and here let's go to the implementation side. Have you learned how to use PyTorch? Some of you guys, right? Yeah. So if you use PyTorch, okay, you just need to have one line of command to define a convolutional layer, which is torch. Okay, torch is PyTorch. NN is neural network. So PyTorch has a library called NN. And with NN, you have many, many different options, like a convolution 2D. You can have fully connected layer. You can use torch NN linear to get fully connected layer, whatever. So conv2D is how you define the convolutional neural network. And it has these number of parameters you can play with. The most important things are the first 3 are the input channel, output channel, and the kernel size. Okay, so kernel size is probably the easiest to understand. So what is the kernel size here? Yeah, you have the flexibility to do kernel size equals to 1, then they only compute this region. Or kernel size 2, they only compute this. Kernel size 4, they have a larger kernel. But typically, if you don't have any preference, 99% you want to do 3. And the remaining things are not quite important, or you don't quite need to change this a lot. Padding typically want to have 1, but you can see they all have default value, means they are not typically required to be like manually defined. Okay, you just use default value, except the padding. That's it. Okay, so that's the convolution. Number of what? Oh, this one, channels, right? You can see here is one example. I randomly grab from a convolutional neural network like UNet. Okay, if you define UNet in the middle, you will have a lot of this kind of lines. NN, convolution 2D, 192, 384. Okay, so these are, what are those? Okay, what are those? Well, probably I should go back to this figure to explain what's going on. Okay, so maybe, yeah, go to this. Okay, go to this. All right. So if I want to define these convolutions, okay? So at the beginning, I can have, let me erase this part probably. Okay, probably I can have another color. Okay, so if I want to define a convolutional layer like this, and this is my input, this is my output for the network. Remember, I have NN convolution 2D, just as it convolution 2D, 3 parameters, kernel size 3. Okay, this is the input channel, this is the output channel. Can you guess what should I put here for this layer? For the input channel, what is that? Any number? Well, this is my input, right? This is a grayscale image. And how about the output number? Any number? It's a number. 24? And 256? Any other number? 4? It's 4. Why is 4? Those are 4 channels because you have 4 filters. Then you get 4 feature maps. So this is 4. Okay, and in the code, you just write another line of code. This is 3, and to do the computation from this layer to this layer. Okay, at this time, what should I do for the input channel? Okay. Okay. That's it. Okay, so with PyTorch, if I give you any convolutional neural network, you can basically spend 5 seconds to write your code, and after you write this, then you just let the PyTorch do the backpropagation for you, and you get all these filters. Yes, you can define actually here, you can define as 3.1 or 3.8, whatever, to have this type of kernel or this type of kernel. Okay. It's totally flexible, but again, if you are not doing if you are not doing publication or research paper, just use 3. Okay, this is already the best practice that people have been practiced for decades. Okay, so let me go back to. Okay, great. Okay, so hopefully now you understand what's going on here. And in a real convolutional neural network, these 3 and 4 are not big enough, so we have these crazy numbers. Okay. All right. Okay, after this, now let's go to the second demo we see here. Okay, so this is, let's see. Do you have the access to another slide, the PowerPoint slide? Yeah, so it's fine. Let me pull out that here. Add a 0, typically add a 0. Yeah, in the few slides I will show padding, but probably we can withhold the padding and then play with a real neural network. Yeah, another PowerPoint. So we have 2 PowerPoints, right? Yeah, it's probably on the desktop. Yeah, another slide. Yeah. Okay. All right. Okay. Okay, this is the demo. Okay, so if you have this slide, you can copy paste. If you don't, you can just type in the link here. Bring this back a little bit. Bring this back. Okay, it's Yeah, let's go to the first one and visit. Yeah, actually, you don't need to type in the following things. You just need to type until this VIS, and you will see all the options. Yeah, I will wait until everyone get into that website. Yeah, for the Zoom folks, I probably copy paste the link to the chat. Yeah, if you don't have. Okay. All right, so I pasted at least the first link to the Zoom chat. Okay, I will wait until everyone get to this website. Yeah, after this demo, probably we can have a break. Okay, yeah. Okay, so if you go to the first demo, you see something like this, okay? If you see this, means you get the correct link. Do you want to see the link again, or that's good? Oh, yeah, that's true. That's probably too small, I don't know. Now you can use your mouse to draw any number, okay? And magically, you will see 2 as your final output, okay? And can you tell which network or neural network it is? This one? And you can move your mouse to see the connections. And you can see the connections of each one. And you can see the connections between this and that. The brighter means larger number. Darker means smaller number. Okay. Can you tell what's this? What's this? It's a 2-layer or 3 layers fully connected neural network. Okay. How do they do is that they basically stretch your image to a long vector. If you move, yeah, you can see it connect to everywhere in the image. Basically, you can imagine it stretch the image to a long vector and connect to the next layer. And then once you have the value of this layer, then they further do this fully connection to get this, and eventually you get this. Okay, and you can erase something to see what happened. They can still, now they tell 3, or you can draw 4. This is demo just for numbers. Yeah, just for numbers. Yeah, if you want to do English characters, probably you need to have few more layers, but it doesn't matter. Okay, so you can play with the model and see how the computer work behind the scenes. Okay, it's just these connections. Yeah, like when I show this in my class, the students sometimes are so excited, say, hey, I write 8, but the computer tell me 7. I say, this is not the purpose for the demo. So the purpose is not test how you can cheat computer, is about understand the connections. Which one? The second guess? Oh, this one. Yeah. Second guess is that, well, you can eventually regard this as a probabilistic distribution. Say maybe 4, they have the confidence of 80%. 3 maybe have the confidence of 15%, something like that, right? So in the computer vision paper, you typically see top 1 error, top 1, top 5, those kind of concept. Top 1 means if your ground truth is 4, you need to predict as 4. Top 5 means if 5 top of a prediction say this is 4, this is good enough. So this is the reason they show this plot. Okay, you can draw a random number and see what's going on. Yeah. Yeah, that's a really great question. So yeah, you just provide some example of 0, some example of O. Hopefully they can recognize. And also you provide the context. For example, the context surround your 0, O. If those are numbers, they probably predict as number. If they see letters, they probably predict as O. So you need some context information. Okay, so fully connected network is a little bit boring, right? So you don't see actually a lot of what's going on. So when you do the training, you get all these random numbers for these layers. And when you draw a 4, they probably tell you it's 9 because at the beginning it's totally random. And but it doesn't matter. As long as you define this is the network I want, then you can trigger PyTorch to learn maybe several minutes, and they can give you all these weights. And the next time we put 4, it tells you this is 4. Okay, so let's go to the more interesting demo. Let me grab this back. Yeah, let's go to the convolutional neural network. Okay, so let's see CNN. All right. Okay, this one is more interesting. Let me still write 2. Okay, I will give you probably a few minutes to play with this. And when you move the mouse to every location, you see the real connections in a neural network. And you can try to understand what's going on by yourself first. Then I will cover some key things here. Okay, maybe 3 or 4 minutes. Yeah, this is the real convolutional neural network. Hmm? Oh, yeah, of course, of course. Let me share the link. Okay. Hey, no. Yeah, convolution neural network, yes, okay. Oh. Okay, seems you guys start feel boring, right? And anyone can cheat the computer. Yeah, it's actually surprisingly robust, right? Even with only like a 1, 2, 3, 4 convolutional layers and the 2 fully connected layers, this one is already quite robust. Okay, and let's see what's going on here. First of all, the connection of convolution layer. If you click left button, you can see the real computation here. And oh, let me. Okay, on the right side, you see is the 5x5 kernel. Okay, why it's 5x5, not 3x3? They just want to make this demo more understandable. Okay, so the right side is the kernel, the left side is the real image patch you see here, and they tell you the output. Okay, it's more complicated than the 1, 0 that we did, but mathematically they are the same. If you have a calculator, you can get the outcome. Okay, and when you move, right, you see they just apply the same kernel to everywhere. And you can see since the shape of the kernel is like this, they are trying to highlight, say, oh, now I see 2 boundaries here, some boundary here, right? And for this one, you can see this a little bit more vertical, so they get some high response here. Okay, and you can see it's no longer fully connected. So every time you just compute these smaller regions. Okay, and then, as I said, in the second layer, this one is your input. You no longer directly get information from here. Then you get information from here. Okay, and in the third layer, humans start to lose the control for what computer learned. Right? So they learn all these things, assemble this, eventually tell this is true. So our understanding is probably stop at here. Yeah. Which one? This one? This one? Okay. Yeah, this is just the number I draw. Oh, okay. Okay, let me open this. Oh. Oh. Okay. It's very sensitive. Oh, okay, okay. Oh, this one, calculation? Yeah, this is just some output. Okay, so this is just some output. And this number, this one? Oh, tangent edge. Yeah, this is I think activation function, something like that. The activation function. So I will cover that later, but it's just some, remember, I have something here. I put it something here. It can be something here, can be something here. That's the activation function. Okay, so this is the demo. Yeah, this. Okay, so we probably how long the break should be? 10 minutes? 15 minutes? Okay, great. We have 15 minutes break and go back. Okay, welcome back. Yes, I see a lot of you guys have already got your energy, your food. Then you can have another hour of high performance computing. Can people hear me online? I think yes. Already. Okay, okay. Hello? Hello? Yeah, it should work. Okay, yeah, can I go back? Not this one. Yeah, probably need to click this first, then it will work. Okay, great. Maybe share the second screen. Yeah, share the second screen. Yeah. Okay, it should work. Okay, great. Okay, with some food and a drink, we can have another hour of computation using our brain. It's very energy efficient. Okay, it seems stuck a little bit. Okay, all right. I think we have already covered the three most important features, input parameters, in-channel, out-channel, kernel size. And if you do 3x3 kernel, if you have just one input channel, one output channel, this is the math that we already practice. Okay, so you can see if the green color is the kernel, the blue color is your input image or input image feature, and you get the output. Okay, and as I mentioned, there can be different setup. Grayscale is one channel. RGB, you have 3 channels. And in the middle of the neural network, you may have 4 channels, here 8 channels, any number of channels, but you just apply the convolution on those features. Okay? And you may wondering, well, if I have 3 channels, how can I do that? So basic idea is that you learn 3x3 by 3 3D convolution kernel and apply to your 3D input. Okay, you just no longer just learn 3x3. Now you learn 3x3 and another 3 these 2 filters. Then you can do the convolution operation for RGB image. Okay, and if you have 4 channels, you do 3x3 by 4. If you have 8 channels, you do 3x3 by 8. So those things exactly corresponding to the parameters you set. If you tell PyTorch, say my input channel is 3, then they will generate 3 channels for your filter. If you say input channel is 4, like we used for human face, they will generate another channel here. It will be generated automatically based on your number. And then the output channels, that will decide how many filters that actually you want to apply. So in this case, you have 2 filters. So the output channel is 2. The input channel is 3 because you have RGB. And if you want to have thousands of filters, you just set output channel to be 1,000 or something like that. Okay, so that's the key parameters. So for example, if you have an RGB colorful image, and you can apply a convolutional function to get 6 feature maps like this. Okay, you apply input channel 3, output channel 6, and you can do kernel size 5. So those are totally flexible. Depends on your choice. Okay. So any question about how to get this? Yeah, these are just the feature maps. There are different names. Someone called this feature maps, feature images, activation maps, activation images, features. Those are just different nicknames. Dilation here. I think I don't even have, probably I have one slide about dilation, but I typically never use that in my life. So you don't need to bother. Okay, so if you want to understand it, then that's great, but I never use that. Again, I never use this. Yeah, so no worry about that, right? So if you do programming, right, for any API, you will see like 8 or 10 different parameters, but typically you only care about the first 2 or 3. So that's the typical story. Okay, great. And this shows, okay, I can have any arbitrary channels as input, any arbitrary number of channels as output. And for the next layer, I can have this and this. And you can have convolution 2D 9, 18, and 3 to do the computation from here to here. And you can have convolution 2D 18, 18. And this time, you no longer have 3 by 3 filter. You have 1 by 2 filter. Okay, you can do that as well. Okay, so this is the flexibility you have. And yeah, this is the kernel size. You can see you have the flexibility. You can do 3 by 3. It's like this. This is your input. This is your feature. Or you can just do 1. It will do something. It's basically do nothing, but you can do that as well. Okay, you have the flexibility. But again, if you don't have any personal reason, just do 3 here. Yeah, yeah. So if 3 is not your lucky number or something like that, you can choose another number. All right. Okay. So here's stride. I think we covered the stride very earlier, right? You can tell what's going on. Stride 1 means every time I move 1 pixel. Stride 2 means every time I move 2 pixels. So that's stride. And again, we typically do 1 unless we have some specific reason. Okay. Padding. Okay, so you can see this is the original image, and you can pad the zeros. Okay, pad the zeros around your image. By doing that, if you apply a 3 by 3 kernel, you still get the same size in the feature map compared with your input image, right? You can see here, if you do 3 by 3, the input is 7 by 7, the output is 5 by 5, but sometimes you want to keep the size, so you just add 0 around your input. Yeah. Just keep the same size. Just keep the same size. Yeah, and we want to keep the same size because it's much easier for us to manage the entire workflow. The padding is typically added. Okay, so this is the only thing that we don't want to use the default value. For other things, just use the default value. That's great. Okay, so I think that's all the parameters that I care. So if you want to understand the dilation, group, bias, you can Google what are those. Okay. Okay, so that's basically the convolutional neural network, and the convolution layer is the most important thing here. And I want to show you how CNN and when CNN was invented through this video. Okay, remember this guy, happy face, and he had a computer back to 1989, right? Even before a lot of you guys were born, right? And they put a paper under a camera and click go, and the computer can recognize all these digits.
So that was the aha moment.
Hmm?
That was the aha moment of CNN.
Yes. Right? So this is the aha moment for CNN. You can see, right? Even you provide this, okay, very hard, and they can recognize. Okay, even this. Okay. Very satisfying, right? So, okay, again, happy face, satisfying, and this is his. Yeah, and you can see how bad the computer we had back to that time, right? How happy those guys are when they see this, right? Can you imagine why do they want to do this, right? Why do they want to buy all these hardwares and do these experiments on those digits? Why? It's literally the demo you played, right? Why do they want to do this? Any guess? In what scenario that we want to understand the number, right? They don't even bother about the letters. They just want to understand the 0 to 9. Yes, okay. Who funded that research? Can you imagine? Hmm? Okay, so now you put your letter or envelope under the camera, they can understand those 5 numbers and they can do the automatic distribution of all the letters rather than have a 1 to distribute all the letters. Okay, well, very ironic, right? Today, USPS, I don't know if you have USPS people here, but USPS is famous for slow, efficient, or whatever, right? But they actually made a great contribution to AI and accelerate everything in our life, right? Very ironic. Okay, so that's how they start. And if you talk about AI godfathers, you probably be familiar with these 3 names. Do you know these guys? Okay. Yeah, so this is the gentleman who had the happy face in the video. Okay, Professor Yang LeQuinn. He is professor in NYU and also the chief scientist in Meta. And the middle one is the most famous. Do you know him? Yeah, he just won Nobel Prize last year, Nobel Prize in physics, right? By the contribution of CNN. And these 3 together, they won the Turing Award back to 4 or 5 years ago with the contribution for AI. And the Turing Award is the Nobel Prize for computer science. Okay? And contribution, this make the biggest contribution probably. And Yang LeQuinn's contribution is CNN, okay? If you can figure out, Keras, yeah, that's algorithm. It's more like the application side. But for scientific merit, it's mostly about CNN, right? So you already played the demo. If you can develop the demo back to 1989, you will win the Turing Award. Okay, so that's the idea. All right, okay. And chief scientist at Meta, silver professor NYU, right? So it's silver. If Donald Trump named this probably golden professor, it's silver professor. Okay, all right, okay. And I get a chance to talk to him in conference, and yeah, he is just like Taylor Swift. In academic conference, you will see a line of people trying to take picture with him. So yeah, I took a shortcut, but that's great. Okay, so yeah, this is the thing he won the Turing Award. Okay, convolutional. It's very close to the demo you saw, right? 4 convolutional layers, 2 fully connected layers, and this is the demo when he worked as a scientist at AT&T lab. You can see these are the images we provide. These are the answer. This is the output of the feature map from the first layer, second layer, third layer. It's exactly the same thing you saw in the demo. Okay, and why they cannot recognize cars, trees, do the self-driving, because they have really bad computer back to that time, right? You bring a disk with 3.5K or the bits, and that's basically the thing you have back to that time. But this one is already quite amazing to understand the digits. Okay, and then we will introduce where the deep version of CNN came out. Okay, that was AlexNet. Have you heard about AlexNet? Okay, so AlexNet was the network that make actually deep learning really useful for our real world problem. And if you Google the keyword deep learning, you see this up and down since 2012 or 2010. So here is AlexNet 2012. Okay, remember the time? It's about a decade ago. AlexNet. Okay, and you can see there is a dramatic increase of how people search deep learning in Google. And then another milestone is AlphaGo. You can see they make the curve even sharper, right? The slope is even sharper. Have you heard about AlphaGo? No? Okay. Have you heard about the game Go? Okay, so yeah, this is widely regarded as the most complicated game that humans have invented, right? AI can beat the best chess player back to 20, 30 years ago, right? If you know the story, IBM Deep Blue, they beat the best chess player. But people believe we will probably never be able to beat the best player in this game. But eventually, yeah, they beat the best player from Korea. And you can see this trend down a little bit, and another peak came was ChatGPT. Okay, before ChatGPT, you need to do some programming or do some specific things to use AI. But with ChatGPT, I think a lot of people are using AI right now. Okay, so you can see this is the history, and another thing contributed to the CN side is the data. Okay, so have you heard about the ImageNet dataset? Okay, so Professor Feifei Li, she is a professor in Stanford, and she and her team with many graduate students, scientists, annotate 14 million images with 20,000 categories. Okay, such as balloon, strawberry, or something like that. Okay, so they released this data set even before AlexNet, and they organized this ImageNet challenge, and they want to see how good our human AI is, not human, how good the AI is compared with human back to like a decade ago. Okay, and here I show some examples from ImageNet challenge dataset. Okay, you can see there are 4 categories. They have 20,000, but I just show 4. Okay, goldfish, bridge, spacecraft, whatever. And in each category, the upper one are the easier cases, the lower one are the harder cases. Okay, these are the easier spacecraft, it's a harder. Okay, and I put an error rate here. Error rate means if I throw 10,000 of this image to you and let you choose if this image belongs to one of these 20,000 categories. For example, if I give you a lizard image, you probably classify this as cheetah or leopard or whatever. Okay, then you made a mistake, and error rate means among, for example, 10,000 images, what is the percent human make mistake? Okay, okay, so if you take the time machine back to 2010, okay. So first, let's see how good do you think human is? What would be the error rate for human? They actually did that test with real humans, and they get the human performance as a baseline. What is the human performance? Error rate. Any guess? 0? Okay. 9%? 70? Yeah, this is too weak, right? 70%, which means 8%. 2%. Okay, so we will see. Okay, all right. So if you take the time machine back to 2010, okay, how do you think the performance of AI back to that time? Error rate. Any 30? Okay. 10? 5%? Okay, so 6, okay. Yeah, we don't have any gift, right? So if we have gift, we can give the people who make the clothes. 26.2. Oh. Wow. Okay, very precise. Okay, great. Right, so from this, you can tell the value of this data set, right? Without this data set, you don't have these numbers, right? You can, of course, collect 1,000 images using your cell phone or camera. Then you cannot use that to evaluate the performance of AI and the human. But if you have 14 million images with 20,000 categories, those numbers are actually really persuasive. Okay, so let's see. If you take the time machine, Okay, yeah, very close. 26.2 is very, yeah, very close, right? Yeah, yeah, you probably know that before, right? So you can see, right? So if I give you 100 of these kind of images, AI basically made mistake about above one fourth, right? So it's kind of, AI was really stupid at that time, right? So these images, right? So they made mistake about every 4 images. And 2011, you see, we get less than 3%, 2.4% improvement. And this is what typically happens historically. So every year we get 1 to 2% improvement. And 2012, okay, so again, human error rate is 5%. Okay, none of this. That's it. Yeah, 8 is probably close, but human error rate is 5%. Okay, and AlexNet happened 2012 and reduced the error rate from 25.8 to 16.4. Okay, it's almost 10% improvement. When we see this, right, if you are a computer vision scientist, you can imagine how exciting the entire community is, right? So we never saw this big jump in the history. And everyone tried to download the paper, see what's going on, and try to reproduce their work. And fortunately, this work is really reproducible and really robust. And in the following years, we all follow this design, which is convolutional neural network. And you can see the error rate reduced to 11%, 2013, 7%, 6%, and 2015, literally 10 years ago, that achieved better performance than human. Okay, human is 5. ResNet was 3.57. Okay, so you can see without AlexNet, we probably still above 20% something at 2012. So in that case, you will never have Tesla FSD, okay? So it's impossible. And you can see before AlexNet, these are shallow networks, like 2-layer neural networks, 3-layer neural networks, Bayesian networks, decision tree, whatever. And since 2012, these 2 methods use 8 layers, 19 layers, 22 layers, 152 layers, okay? Deeper and deeper, the performance is getting better and better. And this is the magic, okay? The number of layers, the error rate, 0. 0. 0. You can, now you download any like modern neural network and train ImageNet, you can get 0 error rate. So that's why this challenge died in 2017, because you can imagine those are easy, right? So actually they are not challenging. This is much easier compared with the self-driving things you will have. And Professor Fei Li then organized another challenge with more complicated things. This is actually super, super easy. The image resolution are very small. It's 64 by 64 pixels, something like that. It's far away from our real world scenario, but you can still see how bad the AI was at that time, okay? And this data set is no longer challenging enough for today's AI model, okay? So that's why they decided to stop this challenge 2017, okay? So they have better benchmark today, okay? And all these methods are deep learning methods, all right? So AlexNet is almost, in terms of design, it's almost same as the convolutional neural network that Professor Yang LeCun developed. But Alex probably, I don't know, maybe never win the Turing Award, but Professor Yang LeCun win the Turing Award, okay, because he made the 0 to 1 innovation. Okay, and this is their network in the paper. Okay, so this is NeurIPS paper back to 2012, and they published their network in the figure. And you can see, yeah, some convolution, number of channels, pooling, dense layer, right? And you can see the image seems being cut about half or something like that, right? So can you guess what happened? Why this image is not complete? Why it's not a complete figure in the paper? Hmm? Hmm? Yeah, so you can see, literally, I want to have the complete part here, right? You can see some dashed line to here, but nothing happened here, right? They just rely on your imagination, right? So why it's not, they just need that more space, they can have the complete figure. Yeah, so first of all, the upper side is redundant, right? They just show, okay, you can do the same convolution here and here. The upper figure is redundant. The real reason is that, you know, there is something called the deadline for conference submission. Okay, when they prepare the paper, the deadline probably 11:59, and then when they finish all the paper at 11:30, they realize their paper is overlength about this size, right? So now you have two solutions. One is cut your text, right? Cut some non-important text, but they feel like they don't have enough time to cut the text, so they decide to cut the image. Okay, they just cut the image to fit 8 pages limitation. So that's kind of the thing they did. Yeah.
That involves absolute pooling in CMS.
Yes, so I will cover that concept later. So that is something we haven't covered yet. We already saw that. When you saw the demo, we see the feature map is getting smaller and smaller. That is pooling, but I haven't covered that yet.
Nothing to do with downsize.
Yeah, pooling is just a downsize, Okay. All right, and you can see in their paper, this is where 16.4 came from, and they show, okay, these are the cases, right? Leopard, cherry, whatever. Okay, so here is their network, right? We saw the ugly version, and later people made beautiful version of their neural network. Okay, so first of all, channel, we have covered the channel. So you can see the channel changes a lot, right? From 396, 259, 384, 384, 256, okay? Let me see. Yeah, probably we can play this game again. Say, if I give you PyTorch, can you write several lines of code to actually reproduce AlexNet in a minute? Okay, so here, this is your input image, is 224 by 224 with 3 channels, RGB. And here is your first convolutional layer, convolution 1. Okay? So how would I define my convolution 1 if I have NN convolution 2D? Okay. What should I do here? If I only worry about 3 parameters, what is the input channel? Output channel? Kernel size? Right? They don't use 3 by 3 because that was 2012. But if they publish a paper in 2014 or 15, they will use 3. But that was kind of the first paper. Doesn't matter. 11. Okay. And conv2. Okay. 96. Which one? What should I put here? 256. 5, okay. Then, yeah, I probably do one more. I don't want to do all the layers. Convolution 3. 256. 384, right? 384, 3, okay. Yeah. Yeah, you can, now it's super easy, right? But when I was a PhD student, when we try to reproduce this, we need to use C++ to program all the details of convolution. That was really, really painful. Like it easily take you a few weeks to implement these 3 lines of code. But today, fortunately, you don't need to do that anymore, okay? All right, so let's see, that's the channel. So probably now I give you any convolutional neural network, you can write these channel numbers. Okay, so for example, you can, this is the example we have already saw. Pooling, okay, pooling. So here, you see max pooling, max pooling, max pooling, okay? every time you apply this max pooling, you can see the image resolution is getting about half, from 55 to 27, from 27 to 13. This is max pooling, okay? So first I will introduce what is max pooling. Max pooling is basically downsampling, okay? There is basically no mass here. This is just the downsampling, okay? So in that case, you can see the image, the resolution of the feature map is getting smaller and smaller, but the number of channels is getting bigger and bigger. So you basically want to have more channels, but smaller images or feature maps through the learning, right? So that's kind of the idea. Okay, so before I go to that, so think about it. So why do we want to have a pooling here? Why? Why do we want to have a pooling here? Why? Yeah, implementation is super easy, right? Max pooling or average pooling, but why? Why do we want to have pooling? Yes, okay, so when we understand the object, we first understand the very local features like lines, colors, and later we will have nose, eyes, eventually face, right? Well, if we want to understand the face, okay, let me draw a human face, okay? You start with 3x3 kernels, probably like this. Yeah, you will never be able to understand that this is a human face. You probably find the nose, eyes, mouth. Okay, how can I cover the face? How can I cover the face? I can use a 11 by 11 kernel or 100 by 100, whatever convolution kernel to cover the entire face, right? Right? But what's the limitation here? It's quadratic related to the size, right? So you have, here you only do 3 by 3, so you have 9 weights. Here, 11 by 11, you have 121 weights to learn. It's not scalable for the computer at that time, or still scalable, but very slow, very, very slow. Okay? Then, can you figure out a way to still cover the entire face? Yeah, if you figure out that back to like 13, 14 years ago, then you become one of the most famous people, right? At least in our world. So is there any strategy? Yeah, think about it, we are talking about pooling. Okay, so now I do max pooling or average pooling, whatever, to make my face smaller. And now I still apply 3 by 3 kernel. Okay, another layer, I make my face even smaller. I apply 3 by 3 kernel. Now you can cover the entire face with only 3 by 3 kernel. Beautiful, right? Simple, smart, beautiful. See? The reason is that you want to cover a bigger and bigger region. Of course, you can use larger and larger kernel, but it's computational expensive. So people do a flip away, say, if I cannot make my kernel bigger, let's make my feature map smaller. Yes, you save memory, you save everything, right? You save speed, energy. Now you just need one sandwich rather than 2 sandwiches, right? You save anything. Okay, so that's why they want to understand more and more global features. Like eventually you can see your feature map is 6 by 6, okay? From 227 or 224 to 6 by 6. And the number of features getting more and more because you want to extract more and more information from your input. And this is still the best practice until today. We want to always have smaller feature map, but larger and larger number of channels. Okay, so this is the pooling. And you can see in the code, okay? So if we want to implement the pooling, we just need to add several lines here, okay? NN max pool, Okay, you don't need to worry about implementation. You no longer need C++. You just need to run this max pool 2D kernel size 3 stride equals to 2, something like that. Okay, and here you apply another max pooling, whatever. Okay, so this is the max pooling. Okay, and what are those? What are the only remaining things that we haven't covered? So this is the entire convolution part. Okay, convolution 1 to 5. The only thing we haven't covered is ReLU. ReLU is activation function. So you have, okay, you have NN ReLU here. Okay, so you have ReLU, you have NN ReLU here. Okay, that's it, right? Today, if you give me a network, I can implement that using PyTorch in about 1 minute to write this line of code. Nothing fancy, right? And on the right side is the ReLU activation function. So have you covered the ReLU activation function before? Okay, no, okay. So yeah, have you covered the sigmoid? No, okay. So why do we want to have this activation function, right? So remember when I draw this guy, I say there might be some activation function here, right? This is the plus, and here you have some activation function. Because you want to have some non-linearity in your network. You don't want everything just a multiplication and plus. You want to have some non-linearity. Why? So think about if you have 2 class, I can draw 2 class, okay? Those are 2 class, okay? Okay, if now I want you to train a machine learning model to classify those 2, right? You don't actually need activation function. You can draw a line here. Okay, make sense? But if I want you to classify, again, another data set, okay? Is like this. Okay, so there is no way to draw a line to split those 2. Yes.
So by downsampling
Mm.
this is like
Kind of. You lose the resolution, right? But it's fine because you already got more feature maps. So that feature maps capture those information, right? So if you remember, you get more and more feature maps. You started with only R, G, and B. Now you have 4,000 channels to tell different aspects of the image. Do you see a hat? Do you see a nose? Do you see a mouse? Something like that. Mm. Mm. Yeah, maybe performance similar in terms of performance, but this one probably 100 times faster. So you don't need to wait 5 minutes to unlock your cell phone. You can, of course, use the logic kernel. You should just wait, right? And doing this, you just need a few seconds or milliseconds. Okay. All right. So for activation function, if you have any activation function like sigmoid, tangent H, right? You can make a decision boundary nonlinear. So that's the purpose of activation function. Okay. Okay. So these are popular activation functions: sigmoid, tangent H, like we already saw tangent H in the demo. Sigmoid, ReLU. ReLU is the most popular for deep learning. And we also have some leaky ReLU, ELU, whatever. But all the activation functions are trying to provide this non-linearity for your network. Okay, so this is activation function. Yeah, these are very canonical sigmoid, and this is ReLU. Okay, the red color is the ReLU. Okay, so this is ReLU function. And today, if you are in the deep learning world, 99% you just use ReLU unless you have some specific reason to use sigmoid or tangent H. Just use ReLU. Okay, if you okay, Yes, yes. Okay, so you see the blue curve. Okay, blue curve is the derivative of the red curve. Okay, so if you have sigmoid, if you do the derivative of the curve, you get the blue one, right? And imagine this is something you will do the backpropagation in your path, which means when you pass your gradient from the right side to the left side, you always need to multiply this guy. Okay, and the relu, the derivative of this one is the blue color. Okay, is the blue color. Yeah, this is a little bit abstract, but I try to explain. Okay, so you need to multiply this one. You need to multiply the blue one. Can you tell what's the difference? What's the major difference? Yes, so here you can hit 1, right? And here, if you are lucky, you hit 0.15. If you're unfortunate, you probably hit 0 or something like that. And in the mass, I don't care what you have here. I don't care what you have here. I know you need to multiply this. You need to multiply this. Remember how many layers do we have for ResNet? 152, right? So you need to multiply 0.15 152 times. Okay, so you can use your calculator to see what would you have with 0.5 with power of 152. You can try that now. What would you have? Can you guess what would you have? 0, which means you no longer be able to train your neural network because you always get 0 in the backpropagation. Okay, if you only have 3 layers or 5 layers, sigmoid is much better. You can see how beautiful the curve is, right? You can try, but if you have 152 layers, don't try that. Okay, use relu. It looks more ugly, but you don't lose the gradient on this side. Yeah. Okay. All right. So now we know relu, we know max pooling, and here on the right side is how we do the pooling. Okay, we don't change the channel. Still 64. If it's still 64, 256, 256. The only thing we do is downsample every feature map to a smaller resolution. Okay, and in AlexNet they use kernel size 3, but today we typically use 2. Okay, like this. Okay, so this is all the mass for max pooling. I'll give you 30 seconds to see what's going on here. Max pooling. And I tell you, this is kernel size 2. Yeah. Y is 64, right? Rather than 63, right? Something like it. Yeah, remember AlexNet, our ImageNet challenge. They organize image challenge every year, and then every year you will have the winner, and the people will all follow that model for that year. And based on tons of experiments from high-tech companies, they have kind of unlimited computational resource. They figure out 64, 128, or whatever is the best numbers you want to use, and we just follow. There is no mathematical reason or theoretical reason. Okay, it's just practical, very practical. Yeah, this is the gradient vanishing problem. So that, yeah, so the blue curve causes a gradient vanishing problem. You can see if you apply this blue curve 152 times, you get 0 gradient. So that's the gradient vanishing. Yeah. Yeah, and if you multiply 1 for 152 times, it's still 1. So you don't lose the gradient. Okay, so that's the idea. Yeah, back to this. Can you figure out what's going on here? Yeah, so every time you see this 2x2 region, if you do kernel size 3, basically you see a 3x3 region and pick the maximum value. Okay, that's it. Yeah, how about average pooling? So another average pooling, how to get this one? You just you just add these 4 divided by 4, right? So that's so easy, right? Max pooling. Okay, and by doing this, okay, you have similar to our demo. Okay, you have some feature maps, and eventually human out of control, right? So we lose the control of what's going on here through the 5 convolutional layers. Okay, you can see the resolution is getting smaller and smaller because we have pooling. Okay, so that's the network. Okay, so now if you understand the pooling rule, you can easily write about how many lines? 10 lines of code to reproduce AlexNet. It's 1 minute, but back to 2012-13, it's 1 month of programming using C++. Okay, any questions here? Okay, so hopefully now you have some feeling of these lines of code. Okay. All right. Okay, and in the AlexNet, they also use this strategy called the dropout. Okay, dropout. So dropout is a strategy to prevent overfitting. Okay, so have you heard about the dropout actually? Yeah, someone have heard about that, right? So if you look at all the big innovations in deep learning, they're actually mathematically all very simple, right? Pooling, ReLU, max pooling, average pooling. So they are all mathematically simple. They are nothing fancier beyond the elementary school level math, right? So dropout is another thing. Okay. So think about, so if you have a convolution, if you have a deep neural network, right? Have you heard about the idea of overfitting? Okay, overfitting. So when you have a very complicated model, but you only have few training examples, you will be easily to get overfitting. Any questions about that concept? You have a very complicated model. For example, I give you whatever big model with billion parameters, and I only give you 1,000 training images, okay? And I ask you to train the model to classify cat versus dog, right? Billion parameters for this simple task. Okay, you will obviously get 100% accurate in your training. Yes, so there is a very famous example, like I'm not sure if you saw that, like people train the classifier between different between dog and wolf, okay? Dog and wolf, okay? And here are probably some nice dog, here are some wolf, okay? And when you train the model, you get 100% accuracy, okay? But do they mean you actually learn the difference between dog and wolf? May not, right? So when people do experiments, say they grab a dog and put them into a snow scene, same dog, and they take picture when the dog sit on the snow, and they take pictures sent to the network, they tell this is wolf. The network tell this is wolf. Can you imagine why? Yeah, so you believe the AI is trying to differentiate dog from wolf, right? But eventually, since you have very high number of parameters or weights, they can remember the background. They can remember how many numbers of years, for example. They can remember everything in your training data since you have very powerful network. And in that case, they basically learn some background information rather than the difference between dog and the wolf. Okay, so this is overfitting. Okay, to overcome this scenario, what can we do? Well, actually, the easier way or the better way is to expand your training data. You just collect some picture like this and tell the network these are dogs, right? So that's actually the better strategy. You can further expand your training data from 1,000 to like 1 billion training examples of dog and wolf. So in that case, if you can classify this 1 billion, maybe your network is good enough, okay? And if you don't have that privilege, if you cannot expand your data, then you can think about make your network thinner, okay? I want to use maybe 1,000 parameter rather than billions of parameter. Yeah. Yeah.
I have a simulation type of data, with data,
Yeah.
real life data. My real life data cannot match. And I don't have enough data for the real life data. That time, what would I do?
Yeah, either collect more real data or make your simulation more realistic. Today, Tesla, NVIDIA, for any high-tech company, when they train the self-driving system, they use simulation. I don't have the picture here, but if you Google that, now their simulation environment is just like the real world. So you cannot tell if the car is driving on the real street or in their simulation environment. So one way is to make your simulation as close as to the real world, or you need to drive a car to collect the real data. So either way, yeah.
As a human, we never perform our mistake.
Yes.
There is a simple thing, or we have to go ourselves and get the root cause and put it as a brain.
Yes. Yeah, that's the expertise of Professor Collery. It's kind of robust learning or trustworthy learning. So there are many of the papers talk about the robust AI, trustworthy AI, uncertainty estimation. But this is still an ongoing topic. We don't have the solution. Say now we can avoid this problem. We don't have the solution now. We just try our best. Right? You can see self-driving cars still have accident. Right? So it's still not there. Yeah, but that's a very interesting discussion, right? So it depends on our goal. Are we trying to actually avoid any car accident? Is that our goal? Right? Our goal is that if I have the entire Tennessee people using self-driving car, if the accident rate is smaller than human, that's acceptable, right? So that's kind of the story. Right? We are not actually targeting zero accident. It's probably never happened. But if the human accident is 5 in million, I don't know, every day. If the AI is 5 in 10 million, that's good enough, right? That's what we are pursuing. So that's why we want to have the human performance here and try to beat the human performance. So that's kind of our goal. Yeah. Yeah, dropout is like you just try to make your network thinner, right? Yes, you can set the percentage you want to drop out the nodes in your network. You can set 10%, which means I randomly throw out 10% of the parameter. You can set 99%. It means every time I only keep 1% of the nodes. So you can set that as a parameter, right? So you can see, I probably have it in the next slide, so you can set the parameter. I saw some, yeah.
Yeah, so I was asking about
Yes. Mm. Yes. Yeah, the goal is to have your distribution. You have a training data set, right? The goal is to have the distribution as close as possible to real distribution. Okay, if you have these kind of variance, for example, dog and wolf, they will not have 3 years, right? You don't need to worry about that variance. So if your distribution follows the real distribution, your model will be more generalizable. So that's the idea. And in the real distribution, you definitely have some dog sitting in the snow. That can happen. But if that's not included in your training data, that's the problem. Right? You don't see a dog sitting on Mars or Moon, right? That's fine. So yeah, so that's kind of the idea. Yeah, exactly. Yeah, there are a lot of interesting discussion or argument. But the idea is for dropout is that if you don't have the capability to scale up your training data to your model complexity, probably you can reduce the complexity of the model. Yeah.
Question about the dropout.
Yes.
How do you calculate how many neurons you drop out? Is it kind of trial and error, or?
Yeah, just try it. You try 90%, 80%, 50%, 20%, and see what's going on. And again, don't forget we have ImageNet challenge, right? If one model win the challenge that year, they use 20%, then probably we use 20%. Okay? All right, so that's the idea, right? So now you can make your network thinner, right? You don't need to have all the connections by doing dropout. Okay, and the beautifulness of dropout is that in the training, you randomly drop out the node, okay? You don't tell I drop out this first half, then second half, you randomly drop out the node in the training. Yeah.
So if the dropout is random, if you have one run that's finished.
Yeah, maybe, but I think about it, you train this 1,000 iterations or 1,000 epochs, right? So you basically cover all kinds of situations, okay? So, and there is only one parameter you need to tell dropout is that what's the percentage to drop out? 20%, 50%, 80%, right? And if you drop out those nodes, you have a very sparse neural network. Yes, in the training, in the testing phase, you don't need to do dropout. You still use the. Yes, if you drop out that node, the backpropagation will not go through that node. Okay, so that's the idea. So now you have a thinner neural network, and you use this in the backpropagation for this iteration. Okay, and for every iteration, we will resample the nodes. It's not like, okay, for my task, I keep this network. It's not. So next iteration, I probably drop out this guy, drop out this guy to have this random dropout. Yes. Yes. Yeah, if this node is not selected in dropout, in this optimization, you just keep your previous weight. You don't change it. But if this one is selected in dropout, you update the weight. Yeah, remember this. Yeah, you don't want to have a random number. Otherwise, you will have a random network eventually. Yeah, don't make it zero. Yes. Okay, it's just like make the training more difficult, right? A lot of athletes, they just make the training more difficult than the real Olympic games they will have, right? If you want to run, I don't know, 300 meters, you can put some heavier things on your leg and run, and hopefully when you run the real game, you can perform better, right? So like NBA player, they probably play 5 hours rather than like 48 minutes in the practice, right? So that's the intuitive reason. Okay, so this is dropout. Every iteration, you randomly drop out some of the node. Okay, this is actually a very good strategy. For example, I see you have a team of 4 students, right? So if you are taking this class and I say, we will have a final project, okay? So very likely some of you guys will disappear in the middle of semester and one guy will take over all the jobs, right? But if I tell you there will be random dropout, which means your teammates may randomly disappear in the final presentation, then you will try your best to actually do this by yourself. And eventually in the testing stage, I allow 4 of you guys work together in the presentation. You will have a much better presentation than the previous strategy. So if you're a professor, you can introduce dropout in the classroom to encourage people to make their own contribution. Okay, right? So you can feel like if you have dropout, everyone will become a better node or better learner. Okay, so that's the case.
But you don't drop out unless you go to the model.
Yes. But today, typically you will overfit your model because it's way more difficult to collect more data than scale up your model. Yeah, scale up a model, you just buy more computer, build the computational cluster. But to collect more data, you actually need to have a lot of human resource human cost to collect those data. Different. You can see you have random dropout. You don't make dropout once at the beginning and keep that network. It's not, right? If I tell you, for example, you have 4 students, I tell you 2 of you will be disappeared, then it's still the issue, right? For the remaining 2, I probably rely on my teammate. But if I tell you it's randomly dropout, you don't know who will disappear, then you need to work harder. Yeah, the training accuracy probably a little bit lower, but the testing accuracy will be better, much better. Yeah, you can reduce the overfitting with dropout, right? You can see now you have smaller parameters.
So if the parameter is smaller, but accuracy more than the earlier, right?
Yes, another example I can give you is that, yeah, I was an international student, right? So when I came to US, one of the first restaurant I went to was Subway. I never got so many questions in my life to order a food, right? So what kind of bread do you want, right? Italian, whatever, right? So what kind of meat do you want? What kind of vegetable do you want? What kind of sauce do you want? Do you want to bake it or not? As a new international student, I don't know most of the things, okay? I probably just do this, right? And they teach, oh, do you want Italian bread? Oh, this is called Italian bread. And then I remember that, right? So think about if I go to the restaurant 100 days, if they prepare all the food or all the ingredients, I probably always order Italian bread, ham, banana pepper, mayo. That's my sandwich. I will never be able to understand the name of the other ingredient, right? But if they do dropout, every day they randomly drop out 20% of the ingredient. They will enforce me to remember everything. Otherwise, I cannot order a sandwich, right? So that's the power of dropout. Yeah, I overfit. Yes, I overfit to one type of sandwich with Italian bread with ham in the middle with some sauce. I get 100% success rate if you count if I success order the sandwich or not. If you count that, I get 100% accuracy if I go that restaurant 100 times. But do I mean I understand what's going on? It's overfitting, okay? I overfit to this one type of sandwich, okay? And if you go to another restaurant, for example, if you go to TSU cafeteria, they don't have Italian bread, then you get 0% accuracy, right? Yeah, you cannot make any sandwich, right? But if you introduce dropout, you can imagine my learning will be very, very robust. Yeah, of course.
So yesterday, you had a line of height, right? That's centimeters. You have those data points and then the line. But why did I do line? I could have done a very high dimensional curve, exactly matching all those points, right? Well, I could have 100% accuracy there, right? But only for the data that I have. Now, if it's a new data, that will be definitely out of that curve, is that right? That's overfit because I use my training data to the perfect match. But that perfect match will not work with the new data, testing data. So with overfit, it will come out. Instead of doing a high-dimensional, exact, correct matching to training data, I want to do less perfect, but it will work better with the real world data. You understand? That's the purpose of it.
Yeah, exactly. Yeah, so, yeah, this is kind of the concept has been repeatedly used in different machine learning strategies. It's not something new, but remember AlexNet pushed the error rate from 25% to 16%. So this is one of the reasons. Not only they make Professor Yang Kun's ConvNet with more channels or higher resolution. That's one reason, but this is also another important reason. They can push the error rate 10% down, dropout. Okay, so that was in their paper if you're interested in. Okay, any question about dropout? All right, let's see another important trick they make, okay? They introduce the strategy called the data augmentation. Okay, so can you tell what's going on here? Yes, right? So remember, it's still the difficult thing is it's difficult to collect more data, right? But can we make our data intentionally more variable or more complicated? They propose, not they propose, they use this idea called data augmentation. Okay, so for example, suppose this is your cat. Okay, suppose this is your cat. If I flip your cat, can you still differentiate with your cat with your friend's cat? Can you still do that? Yes, right? But if the deep learning model cannot do that, which means there's something wrong. They probably look at the background rather than look at the features of this cat, right? And to prevent that, I would just flip my cat and put that into the training data as the 1001 example and give the label, say this is my cat. Okay, and here is another strategy that you can randomly crop your cat from the big image. Your network should still recognize this is your cat rather than your neighbor's cat. Okay, by doing this, this probably improved like 2 to 3%. This improved 2 to 3%. The ConvNet improved 5 or 6%. Then you add them together, it's your 10%. Okay, so this is the third important trick in the AlexNet. Okay, and those tricks are still used today, still using today's state-of-the-art convolutional neural network. Yeah.
So in data augmentation, be a replacement for adding more training data?
Well, so it's always kind of there's no free lunch, right? There's no free lunch. You can push your performance from 85 to 90 maybe by doing this, but you will never hit 99, right? So there's no free lunch. It's a strategy to improve your performance, but if you want to fundamentally improve your performance, then you still need to collect more data. But once you collect more data, you still want to do data augmentation. So this is a strategy you will use anyway, right? So it's done to say if you have 10 times more data, you don't want to do augmentation. It still gives you benefits. Why not? Yes, 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 right? So this is something cheap and it should work, right? So if your network actually remember this is your cat, as a human being, there's no way say, if I rotate my cat, if I flip my cat, if I cut some piece, I cannot recognize this is my cat, right? But if AI cannot do that, there's something wrong in the training. Okay, and this one compare the LeNet, okay? So this is the cool thing in academia that you can name anything you want, right? Alex named the network AlexNet. Yang LeCun named the network LeNet, right? You can name like a PeterNet, DavidNet, whatever, and keep that in the history by thousands of years, right? So something like that. You can see in terms of network design, there are nothing different, right? Few convolutional layers, in the paper of LeNet, they call this subsampling, but this is literally the pooling, okay? And they have few fully connected layers, okay? But now, not now, back to 2012, you have GTX 580 GPU, but Professor Yang LeCun only have like a 386 or 486 CPU back that time. Yeah, if you visit UPenn, you can still, if you visit their computer science department, you can still see the very original computer, and they have the video and the photo. They show there are some ladies need to plug in and unplugging all the cables to do the computation, right? So you cannot do any deep learning use that machine, right? It's impossible. But with GPU, now we can do that. Okay. All right, so I think that's the last slide. Any questions before we go to the last demo? Any? Flatten, which one? Oh, you mean this one? Okay, flatten, right? So this is something you need if you're doing classification tasks, but if you're doing segmentation tasks, you don't need to flatten. So this is, depends on your task. If you try to classify cat versus dog, you probably want to flatten because eventually you want to make one-dimensional decision. But if you're doing segmentation or object detection, you don't actually need to flatten it. Yeah, so if you do detection, you can probably stop here. Yeah.
I guess conceptually, why do you fully connect the layer?
Yeah, it's the same principle, right? So otherwise, you can ask the flip question. Otherwise, how do you know if you stop here? How can you know this is a cat or a dog? You need to have something to tell you this is cat or dog, right? But if you flatten them and eventually have this 1,000, this is dog, cat, frog, fox, eagle, whatever, 1,000 categories, then you have something can tell you either this is a cat or dog or frog. But if you only have this, how can you tell? This is just a feature map. Yeah.
From yesterday.
Yeah.
Let me test yesterday. Good question. So basically, as Professor explained here, start with an image. Can be a grayscale image, color image, doesn't matter, right? At the end of the CNN, once the training is done, you get a multi-dimensional array. That's, you see right there, 13 times 13 times 12. That's a multi-dimensional array. That's your feature. But you have one more you have to do, that all neural network. Using those features, run the classification. So instead of sending that multi-dimensional array, it's flatten it. That's sample one. See, that's exactly like instead of having that multi-dimensional array, similarly like when you have two-dimensional array converted to one, exactly the same thing. And we can do it.
Yeah, thank you. That's a better explanation. Okay, so you can roughly regard these convs as feature extractor. Yeah.
How do you think about the data quality in the model? Why there is
Yes. Yes. Yeah, there is a very, very famous saying in deep learning is garbage in, garbage out, right? So if you provide the thing actually not good or out of distribution, for example, if you want to predict breast cancer, but you only provide the male data, right? Garbage in and garbage out, you probably have then your classifier to a female patient with actually a big tumor there, you tell 0% because you never see any patient is diagnosed as breast cancer in your training. So it's garbage in, garbage out. So you need to prepare your training data as close as possible to your real problem you want to solve.
How do you feel about the zero-shot line and the few-shot line? Put a lot of libraries as well as some good data.
Yes.
Just throw some.
Yes. Yeah. So zero shot, it doesn't mean they haven't been trained. They have been trained with ImageNet or another bigger training data. Then their claim is that you can use this to a field that was not in the original training data set. For example, if you train an ImageNet challenge data set with this sound category, right? They can understand the leopard, lion, whatever, but you never had a tiger in the training data. In this case, you can reuse this model with some trick, either zero shot or few shot, to provide maybe 1 or 2 tiger images and tell them, oh, this is something different from your training data, then they can perform really well on tiger if you only have 2 tigers images.
you also take the liberty of using any data.
Yes,
Training.
yes, yes.
And you don't care if some data is very highly out of distribution from your intended data.
Yes, yes. But again, there is no free lunch, right? So of course, you can use all data, but now train a big, large-scale model takes like $5 million, $10 million. So there's no free lunch, right? So if you know your performance will not be much better or significantly better with this more collection of the data, why you want to do that? You still want to carefully select the data of the training, right? For NLP, this is a little bit different because today's large language model like ChatGPT or any large language model you are using, they basically use all available corpus. They just download all the text from internet, from library, from whatever, just train that. Because the language has a way smaller solution space than image. Language is decided by human, right? So if I have a sentence, thousands popular English words, 60,000, I don't know, but it's a finite space. And the order also matters, right? So for any sentence, if I flip the order, you don't understand what I'm talking about, even with the same words, right? So in that case, you are dealing with a smaller solution space. But for visual signal, you have no control. Everything you see here are not made by like a human rules or something like that, right? You see a mountain, why the mountain is the Smoky Mountain, like a Smoky Mountain. It's made by some superpower, right? I don't know, God, alien, whatever. It's not made by our rule. So that's a way more complicated problem to solve. So that's why we still don't ChatGPT for vision. We don't have that. No, it's kind of if ChatGPT is, I don't know, is adult, vision transformer is vision transformer, the maturity of vision transformer is probably 1 month, baby. Yeah, with the current learning strategy, probably will never be able to achieve. I don't know. It's my personal opinion. You probably will never be able to achieve ChatGPT. Right? You can see it's a significant, more complicated problem. Right? Mm.
Sometimes feel that the model is already shifted towards the cyber.
Yes.
Fine-tuning another data.
Yeah.
It might be more complicated or more time-consuming to go to the convergence data rather than starting from.
For specific purpose, computer vision has already been there, right? Self-driving is there. If you do self-driving, if you do face recognition for your cell phone, it's already there. Works really well. If you do the surveillance to count the people, it's already there. If you put the vision system in the manufacture, agriculture, whatever, it's already there. But there is no generalizable AI that you train the model can do all these vision tasks. It's impossible right now. But for ChatGPT, you can use that to translate, extract the keywords, help you make a fiction. You can basically use that for any language task you want. So far, I don't see any tasks that I want to do with my language that cannot be done by ChatGPT, right? For example, in the future, if you have whatever vision model, it can basically understand all the visual signal. That's kind of ChatGPT, but it's still not there today.
Along the edges, when you have the features to be, because it has the edges around, right?
Yes.
It's not a full picture.
Yes.
Where is this actually? So from that node, whatever image you have, don't you think that these edges might be kind of mapped to these new images and can be better?
Again, I'm pretty pessimistic about that, right? So it's still the philosophy problem. You are trying to understand the world, and you are made by the world. You are made by the earth. How can you understand the earth by something made by the earth? Maybe alien, they can understand us if they live in 5-dimensional space or 6-dimensional space, right? Like, example is ants, right? If you have a table here, and you have legs here, ants live in 2-dimensional space, so they can only do something like this, right? from a three-dimensional species, we feel it's stupid, right? Why don't we just jump from here to here? But they are restricted to their dimensionality, right? If there is an alien, they live in 4D space, which means they can go back forth with the time. We cannot do that. We cannot go back to yesterday. But if they can do that, they can probably understand us. Right? I don't know. So it's already some philosophy problem. Right? Maybe what we are doing every day are stupid from a four-dimensional species. Right? We are basically a simulation. Who knows, right? Yeah. Who knows, right? Unless you are a high-dimensional species, right? Just like you feel ants are stupid, right? But this is how they live. Some questions over there? Oh, you mean the relationship between these two models? Yeah, you can see. Motion here. So. Oh, you mean the difference between these two models? Yeah, you can see this one is deeper, right? In the first convolution layer, you have 96. Here, you only have 6. You only have 6 channels. Here, you have 96 channels. The image resolution is also bigger. Yang LeCun can only deal with 32 by 32 resolution image. And AlexNet can deal with 27 by 227, right? Here, 256. Here, only 6, right? So this is exactly, not exactly, but very close to the demo you played. You only have 4 or 6 channels. But this one is 96. You see tons of features. Oh, okay. Oh, okay. Yeah, for the last demo, you can do that at home or something like that. It's just some existing code. Okay, let me go to this website. So, yeah. No. I think I'm good. I can go here. Okay, so this is the folder. Let me send that to the chat. You can join the Zoom link to get that link. Okay, so this is okay, so this is some example, and yeah, probably I need to switch to Chrome. Okay, but yeah, so this is the complete deep learning code to do some digit classification, right? It has convolution layer, dropout layer, other layers, and with this forward pass, and it included training and testing. So that is the demo that you can basically do what Professor Yang LeCun did using convolutional neural network. And to do that, you just need to run this Jupyter notebook. So this is the Jupyter notebook. And yeah, since this is not Chrome, so probably we cannot directly open. Oh, probably I can do things like that. So we can do, yeah, right clicking. I see what you mean. Right clicking. No right clicking. Yeah, let me drag it back first. Let me see how can I do that. Yeah, probably I need to log into. But if you open that with your Chrome, it should not be problem. You can right click and open with Google Colab, and you can run this main.py. The basic idea is you just need this. Let me put it back. Download this. Yeah, I don't think we have time to actually run it, but I just want to explain what's going on. Open. Yeah. Yeah, anyone actually download this or open that with Chrome, you will be able to see that it's just the 3 or 4 lines of command, and you can basically run this Python file. That's it.